the previous lecture, we had Steve moving pretty much like this. So we have our kind of completed walk cycle, which is pretty good considering we've used 2 curves and an inverse kinematic system to do it. We actually haven't done it by hand. Now, to make it even better and slightly more realistic, let's clamp those targets to the ground plane and also move Steve around within the environment. Okay, so let's get this started. First of all, I'm going to grab hold of my left foot target and just lift it up a little bit and bring it out here. And from here, just imagine that the leg is moved up here and the foot is like sticking out here. What we want to do, first of all, is to clamp these guys to the ground. Okay, so what I'm going to do is use a raycast, a physics raycast, and I'm going to start the physics raycast above the sphere, just in case the sphere is sort of through the ground, and then project it downwards until it actually hits the ground. Now, there's 2 things I have to do. First of all, for these spheres is to turn off their own sphere collider so that they don't get involved in the physics collision. Yes, I could mask them out and do different layers and that, but I'm not going to do that for now. So just select both of those things and turn off their sphere collider over in the inspector. Okay, so let's move this guy back down to where it was before, which was about there, wherever you want it to start from. Okay, so let's go into our Walker code. After we've calculated where we're going to have the sphere, then we're going to come down here and we're going to do our raycast hit if physics dot raycast. Let's make sure that we spell physics correctly. Okay, the raycast, we're going to raycast it from the left foot target dot position plus just up above it in the up direction for it. So left foot target dot up, and then we're going to cast it downwards. So that'll be left foot target dot up, but we want the negative of that. So that's actually our downward ray that we're casting into the environment, hopefully going to hit that ground. We want to out into our hit, and we're going to do a math f dot infinity, which means we're going to project down forever until we hit or we don't hit something in the environment. So left foot target dot position equals hit dot point. And let's do the same thing for the right foot. So we'll just copy that and put that down here and just modify our left to our right foot, negative, right foot, and then we'll set the right foot target down here. Right, so with that down, save it. Let's go back into Unity. We're going to press play and have a look at the effect of this. You can probably already guess what it's going to be. So let's have a look. And we have our spheres back on the ground. So any of that vertical movement we put in before is actually gone. But don't worry, we'll bring that back in a minute. Now, the nice thing about this is if we get Steve and actually move him down, then we now get movement in our knees, because see that the spheres are now sticking to the ground, which gives you a bit more realistic kind of walking movement, because that's what happens when you move. Your knees bend and you're actually touching and moving your feet along the ground. Okay, so let's stop playing. At this point, you could grab Steve and actually move him down just a little bit. So now the spheres will snap up onto that surface and we will get a nice bend in the knees as we're actually walking. Okay, right, great. Now, what we're going to do next is to actually put that vertical movement back in. Okay, so this requires a little bit of re-engineering of the code. We need to figure out when the foot or either foot is moving in the backwards direction. If it's moving backwards, then we want to clamp our end effector to the ground. Otherwise, we want to let that knee lift the foot above the ground. So what I'm going to do up here is I'm going to monitor the direction using the last position of the foot, which is going to be the position of the foot in the last frame. So we want a private float left leg last equals 0. This is actually not the position, it's more of the actual movement of it. So how much is actually moved in the last frame. So private float right leg last equals 0. Okay, now what we're going to do with those values is actually update them at the end of each update loop based on how far the foot has actually moved in the horizontal direction. So inside of the update at the top here, we're going to create some local variables. So float left leg forward movement, and that's going to equal our horizontal curve dot evaluate time dot time, which is the value that we're using to move our left leg forward, which is this value here. So we can actually grab that and replace that down there just to make sure that we don't change that value, and if we do, we change it up here. Then we want the same thing for a right leg. So let's copy that and put our right leg forward movement. Horizontal curve is going to be the same as what we've got down in here, which is a -1 for the right leg. So let's grab the right leg value and substitute that into our little equation here, like that. Okay, and then we want to update this left leg or last left leg value, movement value, at the end of our update loop. So down here, we're going to go left leg last equals left leg forward movement, and right leg last equals the right leg forward movement, like that. Now we can take one away from the other to determine which direction that we're actually traveling in. Okay, so before we bother clamping that thing to the ground, we're going to test if we're actually moving in a forward direction. So we'll go float left leg direction, and that's going to equal left leg forward movement minus the left leg last position. And we want the same thing for our right leg. So right leg direction equals right leg forward movement minus the right leg last value. And with those, we can now test in our physics down here. So we're going to test if we're hitting the ground as well as moving in the right direction. So left leg direction less than 0. So if we're moving backwards, then we will perform this ray cast, and the same thing for our right leg. Right foot target right leg direction less than 0, like that. Now we could even make this a little bit better, in fact, by testing that this happens before we bother doing the ray cast, because we don't want to do the ray cast and waste our energy doing that. So let's just take that and put it up here, and then just put that on the next line instead, because that test is actually going to be a lot more efficient than doing the ray cast. And let's just rearrange this one here too. And bring that up to there. Okay, so let's save that and now have a look at what we get with the leg movements. Now it's going to be subtle because it's not moving very far above the ground, these two effectors, but you will see how they are slightly lifted above the ground when we're moving forward. Okay, so see that they are clamped, but you can see they become above the ground when they're moving in a forward direction. And of course, you can, again, affect those and how high he lifts his legs using the curves. Okay, final thing we need to do is now to get him to actually move forward. So back in the code, where we're going to do this is to push the body forward by the same amount that the forward movement of the leg, or I should say the backward movement of the leg. Does that make sense? If you've got a leg moving backward, it's the one that's on the ground pushing the body forward. Now, we know the direction of travel, of whether one leg is moving in a certain direction or not, based on our if statements that we've got up here. So what we can say inside of this, as well as putting the foot on the ground, is to actually move the body at the same time. So the way we do that is this.transform.position. So we're actually changing the root object. So Steve, okay, the right top of his hierarchy. It's the first time that we've affected him. Because we're moving that now, that's why we've made everything else relative to this and made sure that it is actually a child, you know, all of those other bits and pieces. All right, so we're going to move him by this.transform.forward. So we're moving him in his forward direction, and we're going to multiply that by the amount of movement, which is left leg direction, but we actually want it to be the absolute amount of that. So maths f.absolute for that direction, like that. The same thing you want to do down here when the right leg is on the ground and in charge of moving things around. So let's just put this as right leg direction, like that. Okay, great. So let's save that. We'll switch back into Unity and have a look at the effect of this walk. Okay, now it's probably going to look a little bit stilted because he is taking very large steps, as you could see there as he walked away. So let me just play that again. And there he goes. Okay, so he's actually moving forward, and it looks like he's grounded. His feet are propelling him forward, but they're not. Okay, it's just the mathematics that's behind that and doing it. Okay, so that's our walk cycle. Now, we could make it a little bit better just by tweaking the values that we've got here. Obviously, in this particular case, he's taking huge strides forward, and we don't want him to kind of be stretching that far out in front. The other little issue that we've got, if I just get in a bit closer, is that at points, if I can pause this at the right moment and show you, is because of these target locations and that they're hooked up to the bottom of this particular bone, the feet are going underneath the ground. So you might want to change the target locations for one of these instead. So maybe instead of the bottom of this bone, that you put it at this bone here, so that the foot then stays relative to that. We can also, if you just want to see it a little bit more naturalistically, is select both of those targets and turn off the mesh renderer, which will remove those spheres so that you won't be able to see them. Okay, just before we finish this set of tutorials, I just want to show you my final product. What I've also done and found with these feet positioning, because he's got that extra bone in his feet, on the constraint settings, if you actually maintain target offset and put position and rotation, it will actually make his feet plant quite nicely on the ground. Now, I've also changed his stride down to like 0.6 on that horizontal curve. And if we now play this, you'll be able to see the effect that he's now hitting the ground and it's actually pushing him forward, which looks good. Now, he does tend to pause in between strides, and that will be the amount of curve that you've got in your animation curves. So if you've got a really kind of up and flattening out curve before it comes back down again, it's causing this here. If you want to make that happen a little bit quicker with that pause, then do sort of tighten up that curve and make it a little bit steeper, and that will help you out. Okay, so thanks for watching, and I hope you learnt something about animation curves and procedural walk cycles and animations. He's just about to fall off the edge of the world, which he actually won't, because he's not getting any traction by the downward raycasts on this surface here. In fact, if we actually maybe turn him around, so let's rotate him by 180 degrees. Once he hits the ground again, off he goes. Okay, so I can keep talking for just a little bit till he runs out of some more room. Okay, so yeah, that's it. Now, if you want this solution file with this code and the models and everything that's set up like this, remember that you can always get it by becoming a Patreon, and then you can download this particular package for Unity. So thanks for watching, and I will see you in my next tutorial. If you've enjoyed this video, be sure to subscribe, and you can find us at holistic3d.com, take our full courses at h3dlearn.com, and support us on Patreon.